Chris was educated in California, got in 1989 his honored bachelor degree in chemistry from Yale University. Then in 1995 got PhD in chemistry from University of California at Berkeley under supervision of Charles Shank. And next went for a postdoc to the University of California at San Diego, and worked there under supervision of Professor Ken Wilson. And then he started his own scientific career, working firstly as an assistant professor at the Department of Chemistry, University of Illinois at Urbana-Champaign, and next as assistant professor at University of California, Riverside. And at this place, he then became associate professor and since 2012, full professor. Professor Chris Bardeen is a physical chemist who uses laser spectroscopy and microscopy to study light-induced dynamics in solid-state organic materials. His previous research centered on excited state dynamics in organic photovoltaic materials, including exciton fission and fusion. More recently, he has focused on understanding how photochemical reactions in molecular crystals can generate large-scale mechanical deformations and motions. The goal of this work is to develop new photomechanical materials that can directly transform light into mechanical work across a wide range of length scales. He has co-authored more than 200 papers in these subjects and organized multiple workshops and symposia. He's the member of American Chemical Society, American Physical Society, Materials Research Society. And thank you very much for accepting our invitation, especially that this is so early in California at present. So Chris, thank you, and the screen is yours.
All right, thanks, Christoph. And hopefully you guys can hear me.
Yes, we can hear you, yeah.
Okay, so thanks again. Thanks, Christoph and Paulina, for the invitation. It's great to, to finally give a presentation in Poland, actually, because I've read, for some reason, Poland seems to do very well in crystallography and organic molecular crystals, and I've read a lot of papers, especially from the university, I believe University of Warsaw, where Taraska Turk is. So some very, very beautiful work. So I just want to thank you for allowing me the opportunity to sort of talk to you guys in this venue. And what I'm going to talk about, I put in an outline. There's actually 4 things I want to communicate in the 35 minutes that we've got. The motivation, a brief description of how you could actually make molecular crystals into materials, which is one of our goals. And then a couple of stories about anthracene photochromism, and then also cis-trans EZ photoisomerism, and interesting results on single crystals that we have. So with that sort of ambitious agenda, I will just start by saying we got interested in this. I'm a laser person, and so one way or another, if you do research in my group, you're going to be shooting lasers at something. And we got interested in the problem of using light to fuel motion, and we thought that would be interesting for very small nanoscale devices and machines, and even to the molecular level. I know, Christoph, you got some interesting, pretty nice, interesting work in electrochemical powering of molecular motors, but we like light. And then it turns out that there's even broader interest in using light to replace electrons. And this is especially the case for the Defense Department, where they're very interested in changing out their copper wire to optical fibers. And if you're going to do that, you need to have a way to directly transduce light into work. And that was the problem. That's the materials problem, right? This vision of using light to transport energy, and then once the energy gets there, how do you turn it into some sort of mechanical work or mechanical motion? So that's the challenge. And then the answer to that challenge is chemistry. And certainly chemistry is very good at turning light into molecular work through photochemistry. So on the top, I show a single molecule of azobenzene that undergoes an E to Z or a trans to cis isomerization. A single molecule by itself cannot do very much work, certainly not the macroscopic amounts of work that people, if you want to turn a rudder or lower a landing gear, that's a single molecule won't do that. So you have to scale it up, and crystals, the self-assembly of molecules into crystals provides a natural way to scale up, align, and then sort of amplify the work that's done by a photoisomerization reaction. And so on the bottom, I showed the, maybe my cursor is showing up, just the transformation. In this case, I'm using azobenzene as an example. It turns out that azobenzene by itself, when it's crystallized, is not reactive. So this doesn't actually happen. But because engineers only know that azobenzene is basically the only organic molecule they know, I always use azobenzene as my example for this macroscopic crystal-to-crystal transformation that generates work. And it does that through the change in shape of the crystal. So to motivate this, especially if you collaborate with engineers, you have to have a figure of merit and show that your material has at least the potential to have an improved figure of merit. So on the top, this is just sort of my engineering slide where I have a rectangular crystal that elongates by an amount delta L. So delta L over L is called the strain. And E is the elastic modulus, which is basically a measure of the hardness of the crystal, to put it in very, very layman's terms. And so the work density, the maximum amount of work that you can expect to get out of this deformation, this expansion, is 1/2 E and then the strain squared. So obviously the dependence on strain is stronger. And then you can use different classes of materials, piezoelectric, elastomer, polymer elastomers, and then molecular crystals that we like, and plug in typical values for the strain, delta L over L, and the elastic modulus E. And what you can see is that molecular crystals sort of have a sweet spot where they have a very relatively high strain, but they also have a relatively high elastic modulus. And that combination says that the potential work density contained within a molecular crystal that undergoes some deformation, some strain, some length increase, is on the order of 10 to the 8 joules per meter cubed. So this is an engineering criteria that people use to say, okay, how much work can I get out of a certain amount of or volume of material? And you can see that you gain a couple of orders of magnitude in principle if we could harness molecular crystals. And you can compare this to humans. I have down here your work density for your sort of wet muscles, which are basically polymers, is relatively low, 10 to the 3, 10 to the 4 joules per meter cubed. So we're talking about materials that are, several orders of magnitude stronger than, say, biological muscle, right? So this is, when people say they've done an artificial muscle, it's actually not very impressive because muscle is just not a very powerful material. So this is the motivation. We're looking for a couple of orders of magnitude. We collaborate with Greg Barron, and Greg said, if you have say a photochemical reaction, and in this case, the photochemical reaction we're looking at is this 4+4 photodimerization of 9-methyl-anthracene, but it could be any photoisomerization. You're conserving atoms. You can define basically a Carnot cycle. So this is on the right-hand side. What you see is the analog to the Carnot cycle that you all learned about as undergraduates. Now, in a Carnot cycle, you start at the bottom and you input heat, and then the gas expands. Here, everything is a solid. There's no gas. There's no liquid. It's a solid. You put in chemical potential by doing the photoisomerization. So now you've changed the molecular geometries within the crystal. So those molecules are no longer happy in their original crystal lattice. And so they're going to rearrange. They'll undergo a crystal-to-crystal transformation to a new crystal structure. And that corresponds to the gas expansion in a traditional Carnot cycle. And then you can remove that chemical potential by reversing the photochemistry somehow. It could be done thermally, or it could be done with a different photon. That corresponds to cooling. And then the newly reconstituted reactant molecules, again out of equilibrium because they're in the wrong packing structure, will repack ideally back into the original structure. And so this forms a cycle that you can go around and, form an engine, right? Transform in the Carnot cycle, it's heat transformed to work. In this cycle, it's chemical potential put in by a photon that's transformed to work, right? So very analogous. You can define this, and then you can get things like the amount of work generated by a crystal deformation. So does this work? So let's just take this chemical reaction, and this is a single crystal of 9-methyl-anthracene on the left. We shine UV light on it, 365 nanometers, and that crystal slowly expands. The vertical axis is the C-axis, and it also contracts along the B-axis. So you get a single crystal to crystal reaction. That reaction gives you a 7 or 8% strain, so very close to the 0.1 that I had on my slide a few slides ago. That number, that equation, the sort of engineering slide. So this can be done within a single crystal. That's the proof here, using that same formalism. So this is the observation, like I said, of a single crystal expanding and contracting along its different crystallographic axes. And then it's very hard to directly measure the work output of that single, very thin slab of crystal. But in theory, there's no limits, right? So you can go and you can define, so this is 9-methyl-anthracene. These are calculations from Greg. This was published a couple years ago. And you can see this is a polar plot of the work output of that single crystal to crystal transformation. And not surprisingly, for 9-methyl-anthracene, all of that work, that red area, is being done along the C-axis. So the C-axis, that's the axis where you get the expansion, and that's the axis where you're going to get all the work. And you get much, much less work. In fact, it's negative work along the other axes of the crystal. Now, the other great thing you can do in theory, so we, in the previous talk, we had a discussion about how difficult it is to grow crystals, right? And that is definitely true, but there's no limit in theory. So you can look at different crystal structures very quickly. And what you can show, these are 9AC, 9TBAE. These are different anthracene derivatives that all undergo the 4+4 photodimerization, right? So same photochemistry, just different functionalization of the anthracene, different crystal packing, different amounts of work, 25, 30, 39 megajoules per meter cubed, and also different projections of the work along the crystal axis, right? So chemistry now gives you a way to tune the direction and the magnitude of the work output that you're getting from these crystals, all right, at least in principle. So now we have the full tunability of organic chemistry, and you're seeing these numbers, 39 megajoules, which is 3 times 10 to the 7 joules. Greg has calculated other ones that are well over 10 to the 8 joules per meter cubed. So real theory also predicts these very high work outputs that I sort of predicted earlier based on a back of the envelope calculation. So I think there's a lot of potential work contained within crystals. We typically don't see that work because, as many people who work with crystals know, you shine light on them, or really you just look at them the wrong way. And right now I'm shining light on the same 9-methyl-anthracene crystal, but it's a different crystal. And instead of not doing a nice uniform expansion, it just shatters, right? So you have this issue where you build up stress within the crystal, and instead of doing work, it just does work on itself by rupturing the crystal. And so I want to briefly go over, and I think it's going to probably have to be pretty brief, just how we want to get around that problem. And that's shown below in what I call approach 1, where if you have a very small crystal, they typically don't shatter. They're typically much more mechanically robust. And so the game plan is to make composites of molecular crystals, basically a crystal of crystals, that can be scaled to macroscopic sizes, that doesn't break, and that can be used in practical devices. And so I'm not going to go through this in detail. I just want to show you one example where this actually works, so that there is a pathway to making molecular crystals into devices, practical devices. And so this is an example. We heard a lot about fluorine, so a lot of our molecules are fluorinated. So this is a perfluorinated diaryl ethene that undergoes an intramolecular ring opening, ring closing, in this case, ring closing reaction. When the ring closes, you get conjugation, the molecule turns blue, and you also get a change in crystal packing. So this is the crystal before, and this is the crystal after the ring closing. And what happens is you get an expansion along the A-axis of this crystal. So the intramolecular photochemistry also expands the crystal lattice. And if you can do that in one of these composites, if the bottom expands but you don't get light to the top, you'll have what's called a bimorph type actuator, where the bottom expands, the top does not expand. And to accommodate that, the whole structure has to bend. So this is a bending actuator, not an expansion actuator that I was calculating before, but it still actuates. And so the question is, can you do this? And the answer is yes. So we take that diarylethene, and what my collaborator, we've used a lot of different templates to grow these microcrystals or nanocrystals, but the most recent template we used was a polyethylene or PETE derivative that had a random array of holes. This is a track etched membrane. The polymer itself is crystalline, so it templates the growth of the diarylethene crystals. So what you have is a composite, it's organic, where you have a polycrystalline polymer, and then you have aligned diarylethene crystals. That's the photoactive component that's embedded within the polymer. It's not that regular, right? It's sort of randomly embedded, and you also don't get 100% filling, but you do get this composite with a mixture of the polymer, the polycrystalline polymer, and the diarylethene. And this is before, and this is after exposure to, in this case, 340 nanometers, which was sort of optimized. You can see the color change. That's the photochromism of the diarylethene. You can see the mechanical response, which is the curling, because there's more reaction on one side than the other. And then on the right, you can see the actual work that's done by this bending. This is a 10 micron thick strip, right? So very thin, very small amount of organic, but it can still hoist up, in this case, a polymer microbead, and it can do that reversibly for, in this case, limited by the endurance of the postdoc, 700 cycles. So this, again, the fluorines are sort of key to this robust crystal cycling. So you're doing a crystal to crystal reaction within the polymer, and then you're cycling it back and forth by exposing it to UV and then visible light to reverse the photochemistry. So all of this is just a quick introduction to say we do think that there's a pathway for harnessing these crystal to crystal reactions on a macroscopic scale and doing useful work. The one thing I would point out is this work density, although it is a record work density for an organic photomechanical material, it's higher by at least a factor of 5 than anything previously published for, like, azobenzene-based elastomers and things like that. We're still at least 3 orders of magnitude below the theoretical limit for these crystals. So we have a long way to go, and there's a lot of questions about whether we can reach these 10 to the 8 joules per meter cubed figures of merit that we're claiming. But as long as they keep funding us, we'll keep trying. So with that, I want to just shift gears a little bit and talk about the chemistry. I hope, the first part was just, sort of the device part, which is sort of inverted for talks. And then the second part is going to be more about the detailed chemistry. And I want to talk a little bit about the types of photochemistry that you can get that can go on in a solid state matrix or a solid state crystal. One is called basically a negative photochromic reaction. And this is where the photochemistry destroys conjugation somewhere in the system. And when that happens, you lose the absorption, in this case, the absorption in the near UV, because we're losing the anthracene conjugation for this 4+4 photodimerization. We lose the conjugation, and the product absorption is very blue shifted compared to the reactant. And that the advantage of that is the reactant just moves out of the way. Once you photolyze it, the reactant moves out of the way, and you can photolyze the next layer and the next layer and the next layer, and you can get 100% reaction even in an optically thick crystal. So we photolyze, 10 micron thick crystals all the time, as long as they have this negative photochromic property, which is the photochemistry destroys the conjugation. Now, the other option, which is typical of most cis-trans isomerizations, it's also the case for the diarylethene, is when you do the photochemistry, the product actually absorption, it either shifts red or it overlaps the reactants. So in other words, you do the photochemistry, but the photoproduct is still absorbing, and you can't penetrate deeply into the crystal. So in this case, you're often lucky if you can get a micron deep before you're just limited by the light penetration, because your photoproduct is still pulling in photons, and in some cases, it's actually reacting back the other way, and reversing the reaction completely if there's good overlap between the product and reactant. So these are sort of two classes of photochemical reactions that we can use inside a crystal. And now the next part of the story is to just say, okay, here's some examples of how both of them could be useful. So for the photodimerization, it turns out that you can design a crystal with hydrogen bond motifs. That's these carboxylic acids. Then we add the fluorine. And the reason we add the fluorine is we don't know. It just works a lot better with the fluorine. It's more stable, and also the crystal is more elastic. So adding one fluorine, we just heard about the magic of fluorine, and hopefully some of those mechanisms pertain here. But we often fluorinate our compounds because often they perform better with the addition of one or more fluorines. You saw that as well with the diarylethene that was decorated with many fluorines in the top ring. So here we've designed this molecule. The fluorine is for stability and elasticity. The carboxylic acid group is to enforce this sort of head-to-head packing, basically in hydrogen bonded stacks, which I'm not showing here, but you'll have to take my word for it, is there's a hydrogen bonded pair on the other side. This head-to-head stacking destabilizes the photodimer, and so it's reversible at room temperature. So if you do this photochemistry, you create the photodimer, that photochemistry will spontaneously reverse. It'll dissociate back into monomers within a couple minutes. So it's a very convenient reversible system. And the other remarkable thing about this crystal is that if you run the photochemistry, you irradiate the crystal, it does not homogeneously react, but you can see that it reacts according to a front that propagates across the crystal. So it has a sort of unique property that you don't have a homogeneous photochemical reaction. You have a heterogeneous photochemical reaction that happens in sort of different spatial regimes at different times, no matter how you illuminate it. Now, that's very interesting in itself, and I could spend the whole rest of the talk talking about this sort of spatially heterogeneous reaction kinetics. This is just another illustration of what I just showed you, how you're monitoring fluorescence or birefringence, and it just drops at different regions of the crystal at different times as the reaction front propagates across. So these are A, B, C are the different spatial locations. And this has been seen originally by Daiichi Kitagawa, but also by us more recently. And this work was published in JACS just last year. Like I said, the kinetics by themselves, very interesting. I'm not going to talk about that here. I'm just going to say, if you look at this data, what it's telling you is within this 4F9AC molecular crystal, you can have a region that's completely reacted with product and completely unreacted with reactants, and they can coexist right next to each other. And so that says that you can actually, instead of just having the reaction front sweep across, maybe you could actually just imprint different regions of reactant and product without breaking the crystal. The general thinking is once you have reactant and product next to each other, those are different crystal structures and you'll initiate fracture. But that's not the case in this crystal. And in fact, my student Luke showed this. He took a 4F9AC crystal and he irradiated at 3 different locations. So you're not completely irradiating it, so we no longer have the reaction front propagating, but what we do have are now 3 different locations where the crystal has bulged up, okay? It's expanded wherever we've done the 4+4 photochemistry, right? And these are, and they're right next door to an unreacted region of the crystal. There's no cracking. When you turn the light off, after a couple of minutes, the crystal goes back to flat. So you can reversibly imprint spatial patterns into the crystal without fracture, just by using sort of pattern, in our case, 405 nanometer radiation. And the reason it expands, you can sort of understand, is when you get the photodimerization, you get this sp2 to sp3 transformation at the 9-10 positions of the anthracene, and you get what's called the butterfly distortion, where the neighboring phenyl rings of the anthracene sort of buckle up and down. And that happens basically along the c-axis for 4F9AC, and that's what gives you this expansion where you react this column of molecules and they expand slightly above the surface and then contract again after you're done. So with that, we can characterize this basically over time. You get this exponential increase. At the top, you've saturated, you basically reacted the whole crystal. That amount of height change that you get depends on crystal thickness, and it's a linear dependence, and it corresponds to roughly a 3% increase in the height of the crystal along the z-axis. And it doesn't matter if you have a thin layer of gold coating or not. We're irradiating from the bottom, and we still get the same amount of expansion. So we've, like I said, we've varied crystal thickness. Everything is consistent with 3% expansion with this sort of localized excitation. And then the question is, so what? What can you do with that? Well, there are a couple more things. One is, I said before, it's reversible. So here we are cycling back and forth. The purple is UV on. And this is, now we're plotting birefringence. You see the height change or the birefringence. They both happen in parallel. They both indicate that you've had the photochemical reaction. So you get multiple cycles. So it's very reversible system, very robust, again, thanks to the fluorine. And it's very temperature dependent. So this dissociation reaction is very sensitive to temperature. It has a reasonable activation energy. The Arrhenius prefactor is not that reasonable. So it's a little too high. So I'm not sure why it's 10 to the 16. But the nice thing is we can make this very fast by increasing the temperature, and it doesn't have to be a huge temperature increase. 50, 60 degrees Celsius is enough to get reversibility within a few seconds. So now we have a sort of, it's not macroscopic, it's microscopic crystal where we can change the shape reversibly on the time scale of a few seconds. And so what Luke did is he's sort of a nano engineer at heart. So he built on a microscope, because these are microcrystals. On the left is a digital micromirror device. So this gives you shaped 405 nanometer radiation. So that's going to pattern the crystal. Then we have the crystal on a hot stage, so we can raise the temperature, so we can, we can accelerate the dissociation, so we can reverse the photochemistry very quickly at high elevated temperatures. And then we also have a probe laser that comes in from the top that scatters off the top of the crystal. Because if you think about patterning a crystal, the first thing you could think about is if I have multiple ridges, that's basically a diffraction grating. So maybe we can reversibly imprint diffraction gratings into a single crystal using light. So this would be what's called a reconfigurable optic, which is interesting to various people who do, sort of displays and also deformable mirrors and things like that, right? They want to do beam steering on relatively fast timescales. And so this is beam steering on a relatively fast timescale. There are two movies here. On the left is the real space image of crystal. And on the right is the image of the diffracted probe beam. And you can see this is in real time. This is Luke just putting in different gratings. And each different grating gives you different diffraction direction and different diffraction magnitude, depending on the spacing and the orientation of the grating. So again, I'll play the left movie. This is the important one. This is the light, all the different periods, patterning the crystal, and then this is the reversible light diffraction. It's almost done here for the second one for the probe beam. So this is at least possible in principle. This is unpublished work, but it just shows that this system allows us to make some reconfigurable surface that can be updated on a timescale of a few seconds, which is getting close to useful update rates. So the last part of the talk, I want to switch gears a little bit and talk about positive photochromic system, and that is a cis-trans isomerization. So this is an example. This is the first molecule we worked with. DVAM, which is just a divinyl double bond here. This is the bond that switches attached to an anthracene, and we'll see why we like these sort of asymmetric photochromic molecules in a second. But this just shows that this in solution, this is just sort of your standard, very similar actually in many ways to azobenzene, undergoes an EZ photoisomerization in solution. It's at least partially reversible by UV irradiation, so you can irradiate in the visible, and then you can reverse it or partially reverse it by irradiation in the blue. In our case, it should be 405. For some reason, that light is shifted slightly. And so in solution, that's all you do. And if you shine both 405 and 365 or 405 and 532 nanometer light, you get a photostationary state, the sort of standard photochemistry in solution. That's what I'm showing here, just these two rate equations, and the rate equations come to an equilibrium. That's basically the equilibrium constant is just the ratio of the forward and backward rate constants. Again, that's undergraduate chemistry. The way you make this system more interesting is you have to introduce another degree of freedom. And once you have 2 degrees of freedom, you can sort of avoid the stationary equilibrium point. In our case, that second degree of freedom is, I'm calling X, is a mechanical degree of freedom. So in other words, A and B, product and reactant, if you have some deformation, some physical, mechanical coordinate that changes as you add more A or more B, that will change the light absorption, and that changes the rate constants. So note here, I have the rate constants are now functions of X, the mechanical variable, and the mechanical variable, of course, obeys some form of Newton's equations. So now you have a more complicated network of kinetic equations, and this gives you the opportunity to have a feedback loop between the absorption, the photochemistry that's happening in the crystal, and then the mechanical deformation. If it bends, you'll absorb less light, and so that affects the photon absorption, and so you can start to go in this circle. And what that does is it allows you to avoid that stationary one-dimensional equilibrium position that you get with normal kinetics, say in solution or a homogeneous system. And so this is just sort of an illustration to make that a little more plausible. I don't know if it does, where I would start with a crystal, and it has the transition dipole moments oriented vertically, and the light comes in, and I get photochemistry, which is great. That photochemistry does 2 things. It expands one side of the crystal, and it also changes the orientation of the transition dipole moment. So now the crystal starts to deform. As it deforms, it's absorbing less light because it's bending out of the light path. However, it's also orienting the product so that the transition dipole moment is oriented so it'll absorb the light, and so it'll start to reverse this photochemistry. Even though the crystal's twisting, going out of the light, these guys are still absorbing light better because their transition dipole moment is oriented correctly, and you could imagine this sort of rotating in one full cycle around, and that's what I'm trying to sort of indicate here, is that you have a sort of multiple things going on. There's the physical deformation, there's the transition dipole moment rotation, and both of those things together could plausibly give you some sort of oscillatory motion. So this was the guy, and this is the transition dipole moment orientation. This is, we actually start with the cis isomer in this case, and it rotates to the trans isomer, and you get a rotation of the transition dipole moment. We're assuming that the anthracene stays the same, and we're just rotating this conjugated tail that's rotating within the crystal frame, right? So none of this would work if you weren't in the crystal, right? It's the crystal that gives you this preferred orientation of the transition dipole moment, that gives you the anisotropy that you need. And you have to grow the right type of crystal. That crystal is going to be very long and thin because you need to be able to bend it. It needs to be able to deform. And it turns out it's very hard to deform like big square block-like crystals. So the crystals that you want for X-ray diffraction are not the crystals that you want to demonstrate mechanical motion. But this is an example of one of those wire-like crystals. This is conformed of cis DVAM. This is irradiated simultaneously by 2 lamps. So CW irradiation 405, 532. The crystal is oscillating back and forth. That oscillation is due to oscillating populations of the Z and E isomers that are driven by this combination of wavelengths. And this is, moving the microscope, but you get this oscillatory motion. And you can also confirm that this corresponds to a change in the crystal structure. This is a birefringence image of a very similar crystal, not the same crystal. This is also a microwire. And what you can see is the birefringence, the crystal is not oscillating as dramatically as the previous one, but the birefringence is also changing in an oscillatory manner because the crystal structure is changing, because you're getting more E versus Z as you cycle back and forth within this. And again, you have to see this, you have to have some sort of ability of mechanical motion to couple the light absorption with the chemical changes happening inside the crystal. And so the last part of the talk is I'll skip over some of the mechanism. This is just saying that it is consistent with the dipole, the sort of transition dipole mechanism that we said. It also saturates with light intensity, which basically says it's not a thermal artifact, and this is also happening in water, so we don't really have the opportunity to build up heat. But the last thing is we realized that what we really want is, you know, completely the opposite of what we were saying. We want to use a single wavelength to drive this. To use a single wavelength to drive this photochemistry, we want the E and Z isomers to have the same absorption, right? We're not concerned about data storage or anything like that. We're concerned about just driving the back and forth isomerization. So Robbie, my collaborator, developed this derivative. Again, we get this is actually, again, a cis to trans isomerization. It doesn't look like much, but it's actually at the chemical level, it's a significant level, change in geometry. But the absorption of the cis and trans isomers are almost perfectly overlapped. So now we can drive both chemistries easily with a single wavelength of light. And the one caveat here is that you do see polymorphism, actually for many of these molecules. I sort of skipped over that. And so one key is to grow the right polymorph. This is the wrong polymorph, where the isomerizing tail is going to bump into the neighboring anthracenes. The right polymorph is one where you basically get this head-to-head stacking, and all the isomerizing tails are lined up, so they give each other room to move. When one moves, that gives room for the others to move. And then again, these are single crystals. These are two examples of single crystals of polymorph B, the good polymorph, that shows we can grow them in sort of well-faceted microwires. These are SEM images. And indeed, under a single wavelength illumination, these guys will just oscillate away. This is a twinned crystal, so it had two ends, so it's very easy to see its motion, but you can also see other crystals moving in and out of the frame. And again, this is single wavelength illumination from just a light from your microscope that makes these guys move around. You get the same saturation behavior. The dipole allowed nature, the polar plot's not quite as good. We think we understand that. But then the last part is these guys are very robust oscillators. So this is under solar irradiation, so a higher intensity solar simulator. But this is broadband irradiation, and also you get this sort of oscillatory motion, in this case bending. It's trying to twirl, but it looks like a bend. And this is under broad wavelength light. So even at sort of ambient solar intensities, you do see motion under a microscope for a solar simulator. So this is relatively high, but at lower intensities that correspond to your sort of daytime illumination, you will still get motion. So this was also published last year, just to sort of demonstrate that you could get this type of molecular crystal motor type motion. So with that, I'm going to just sort of stop and say, you know, there's a lot of potential work density in crystals. We think the way to get it out is these composite approaches, but in the meantime, we're seeing a lot of very interesting and unique photochemistry and photomechanical response from these crystals, both for negative photochromes with the diffraction, and then the positive photochromes with the feedback loop that gives you light-fueled motion. So with that, I would just want to briefly thank the people who did this work. Fei Tong is now a professor in China. Rabi Al-Kasi is our he's a longtime collaborator in Saudi Arabia now, who really master of organic synthesis, very creative person. The diarylethanes, Daiichi Kitagawa in Japan, and the Kobataki group. Ryan Hayward, I mentioned the work that we did with him. That was part of an ONR Muri. Luke and Kevin are the two grad students who did the 4F9AC crystal work and then the ADT oscillating crystal work respectively. So these are the two key guys who did that work in the group. So I want to thank everybody, but especially you for your attention. And with that, I think I'm done. All right, thanks again.
Thank you very much, Chris, for this really excellent lecture, which is now open for question and comments.
We have one question in the chat by Daniel Kamiński. Have you tried introducing domains in your crystal? For example, similar to those changing polarization with alanine in DTGS crystals in infrared detectors to increase the response of crystals to illumination? So
by domains, you mean, I'm leaving the talk up, but I mean, do you mean co-crystals, or do you mean some other type of additive to the crystal? The short answer would be no. Actually, we've just done neat crystals, but
Other molecules, he's answering.
I see. Yeah, so the answer is no. We've only done neat crystals. There was some very nice work. Masaharu Iri was another guy who pioneered photomechanical crystals with diarylethenes. We sort of came to this, sort of at the same time with different photochromes. And he had a lot of success in making co-crystals, in particular fluorinated with like fluorinated naphthalenes, even unreactive molecules that would improve the response. And so we have not tried that, but that's definitely an avenue that showed promise. And if I had more people, I think that would be a good approach. I mean, one thing you could imagine is putting in light harvesting molecules that that would increase the effective absorption coefficient or would change the optical properties, and then funnel that energy to the to the reactive molecules. But we have not tried that.
Like in photosystems, in
exactly.
biological systems.
Yeah.
Yeah.
Another question by Hans Bedbirgi. How dependent are local and global crystal properties on the density of crystal defects?
Yeah, so great question. And again, the short answer is we don't know. There is variation between crystals, although we've gotten rid of a lot of that, especially with the oscillating crystals. So, our thinking is that it's not that dependent on the defect density, unless you have very high defect densities, because we do get similar behavior. The real variation in behavior is due to the crystal, we think, the crystal morphology. In other words, the habit or shape of the crystal, if it's thicker, if it's longer, that will have a big effect on the response, either bending or expansion. But we don't see we don't think there's a big dependence on the defect density. And the other reason I say that is we did do measurements on crystal expansion, and we just looked at different crystals. This was for the 9-methyl-anthracene system. And all of those expansions, the rates and the expansions were the same to within, say, 10%, even with different crystals. So either all those crystals had the same defect density, or it's relatively robust with respect to defect density. So in other words, we have done experiments where we go to different crystals and showed that as long as those crystals were grown the same way and have a similar shape, they have a similar response. Now, whether they all have defects, and that's what's limiting us, is a separate question. And we probably won't know that until we get closer to the theory benchmarks, right? The theory obviously is done for a crystal without any defects. And so if we find that we're still a factor of 10 below the theory when we get to an apples to apples comparison, then I think we'd have to look a lot more closely at whether defects are playing a role in limiting the response. So I guess we're not there yet in terms of our comparison of experiment and theory.
Mm-hmm.
So you rather expect that defects are lowering your response, but there are some examples where defects are needed to have any response or something.
That could be, yeah. I think of them as lowering the response, at least from a fatigue type idea, which is that the defects would basically allow you to have a different crystal domain or prevent recrystallization in the original orientation. But when you say defects are needed for a response, are you saying for a mechanical response?
Yeah, well, yeah, I don't remember, but
okay.
Yeah. But there were examples where defects were responsible for the macroscopic properties.
Well,
or initiation. Yeah.
Initiation for sure. So I agree for initiating photochemical reactions, like in the example that I showed for the 4F9AC, where the reaction front swept across the crystal, it always starts at an edge, and that's probably because that's where there's free volume, and there's probably also a higher density of defects. So certainly for photochemistry, and then there are many examples of non-topological, non-topotactic photochemical reactions in crystals. Where defects are the key, right? Without the defects, you won't get the chemistry to initiate at all. But the problem with those is once you do the photochemistry, say 9-cyanoanthracene is a great example from, Aldo Briante did a lot of very beautiful work with that system, as have other people. Once the defect initiates the photochemistry, it's difficult to go back to the original crystal structure because, you sort of change the packing seeded by the defect. So reversibility, I think, becomes a problem if you're completely relying on defects.
Chris, you observe, you confirm your photochemical reactions at the structural level. Why not at the level of changes of electron density? I mean, your crystals are macroscopic, say 5 microns. This is ideal size for synchrotrons. The reactions are not that fast. I mean, they last at least a few seconds, so one can collect really great data. And then one could observe all these changes at the level of electron density changes. That would be fascinating.
Yeah, I agree. I agree with that. I mean, the reality is, if you partially react a crystal, I mean, many people have done this. In Daishi is, whose picture is up here, is one of the people who's collected a lot of data on partially reacted crystals. Panche Naumov and people like that also, deserve a lot of credit for, for doing experiments on mechanically deforming crystals as well. We have mainly done experiments sort of before and after. So the product, and then we photoreact, and then we get an X-ray crystal structure of the product. We haven't tried to do too much during the course of the reaction. Typically what you get is a statistical mixture of the product and reactant molecules. If you wanted to actually see the electron density changing of the molecule while it's reacting, then that's a much harder experiment that you'd have to have sort of picosecond time resolved techniques. But I agree.
Yeah, sorry for interrupting.
Oh, I was just going to say, I agree with you 100%, especially, now that we're seeing some of these heterogeneous reactions, we would like to look at that more carefully and see if there's, say, intermediate packings, intermediate crystal structures between the reactant and the product equilibrium structures that tell you something about how the change is occurring through the lattice. So it's a great experiment, but yeah, we haven't done it, and I'm scared of synchrotrons, so I have avoided it so far.
Okay, you had very good ones in California, so it's just within a reach from your place. Anyway, it would be great to have like more, maybe less planar, but more three-dimensional system substituted with different substituents, and your reaction is going through rotation of one fragment, molecular fragment, with respect to the rest of the molecule. Maybe it would be possible to observe clockwise rotation and anti-clockwise rotation, different, maybe that would like different amount of work, I don't know, different amount of elongation.
No, I agree with that. In fact, you bring up an interesting question that, we sort of, see if I can go up to the structure. So we know that this bottom structure here is the reactive polymorph.
You need to share the screen once again, because.
Let me just, I won't go into presenter mode. I'll just show this bottom structure where the reaction happens. To address your question, Christoph, it is an interesting question. You could imagine that all of these double bonds react, say, in the clockwise direction in a synchronized way. Yeah. So, that would be one question for the reaction mechanism, as opposed to randomly reacting, maybe, clockwise and counterclockwise. Maybe when one reacts, everyone else goes the same direction and it's all clockwise. So that would be a great question that, we might be able to answer using those techniques. So you're going to pressure me into going to the synchrotron, but.
And one more comment from me. Would be interesting to see results of X-ray diffraction during all these processes, because those beautiful symmetric structures are entirely because they are based on Bragg diffraction. Is important is in between the peaks, whether you have diffuse scattering, what kind of diffuse scattering, because that would tell us more about deviations from these beautiful symmetries.
Correlation motion.
And correlation motion, yes, exactly.
I'm not an expert in X-ray diffraction, so that as you can probably tell from this talk, but that's good points. I guess there's probably a lot more information there than just the equilibrium structures that we get out. And I will agree that you get the structure from X-ray diffraction, and you're right, it's a beautiful structure, and then you tend to convince yourself that that's the real structure, right? Or at least I do. But you're absolutely right that there's often disorder, or at least configurational disorder within the crystal, and we kind of gloss over that. But that would be what would be within the sort of diffuse scattering within the peaks, and that's probably the most interesting or relevant stuff in terms of how the reaction is actually happening. So yeah, we have not gone there yet in terms of detailed X-ray, sort of in situ during the course of reaction X-ray measurements. But that's probably, now you're making me think about that a little harder, which is a good thing.
And Chris, last comment from me. Why to make it a little bit more difficult to put it into diamond anvil cell and counterbalance this with pressure, as a function of pressure?
Yeah, I agree. There was a guy, actually, we wrote a long time ago, we wrote a paper with Sebastian Jazowski, who's, was a grad student at that time. And we did apply the pressure to see its effect on the reverse reaction, the sort of this reaction where you split apart the dimer, and that was pressure sensitive even within a polymer. Within a crystal, I suspect it's going to be the dynamics will be very sensitive. And that actually is also important for the mechanical applications, right? All of these are sort of, we haven't really tried to do this photochemistry with applying a pressure load. And the question is whether the photochemistry would still happen once you apply a pressure load, and we don't know. So that diamond anvil cells would be important, or one aspect of trying to do that chemistry, in a practical setting where you're actually trying to move, some mass, which would be applying its own pressure to the chemical reaction. So no, that I agree 100%. Diamond, we have some indications that it's important, and eventually, if we ever get to actuator applications, it'll become much more important to know the effects of pressure on these reactions, forward and backward.
Thank you.
Sure.
We have one more question in the chat from Vitaly. How crystal packing affects photochemical reactions? Probably it's related a little bit to polymorphism, right?
Yeah. I mean, it has a huge effect, and and this is the first example, but it's only one of many actually that we have that I haven't talked about. And our problem Greg did calculations of the energies, the relative energies of the top and the bottom polymorphs, which I haven't done a great job of describing, but they are different packing motifs. One is head to head, one is head to tail. And only now we've done, actually I have a lot of results that I haven't talked about on other variants of this architecture. And it's only the head to head type packing motifs that react. The head to tail are unreactive. So your first problem is, unfortunately these polymorphs are the same energy according to the calculations. So the way you grow them is you just grow them under very different conditions, both reprecipitation, but different solvents or different surfactants. So, but you have to get the right polymorph for the cis-trans, and it has to be a head-to-head packing where the anthrazines are all on the same side. And it's not clear that that's energetically favored by a huge amount. Now, so that's one thing with the polymorphs is you know, the polymorph has to have room for the cis-trans isomerization to happen without undergoing some steric interference. So for example, I talked about azobenzene at the beginning of the talk. That, you know, that molecule in solution loves to do cis-trans isomerization, but in the crystal it's completely dead. Doesn't do any photochemistry in the crystal, and that's because it's packed too efficiently. So it helps to have some extra stuff that opens up some room inside the crystal and allows whatever group that needs to change its geometry to rotate or do whatever it needs to do the isomerization. For the anthracenes, again, I didn't talk about it, but again, packing is key. You have to get the anthracenes close enough so they can undergo the intermolecular interaction. So polymorphism is totally important, and you can have a molecule that's very reactive in solution and completely unreactive in the crystal. And you know, then you have to get to work and try to go other crystal polymorphs and see if you can get it into a geometry where it can react. Now there's one other subtlety that I didn't mention, which is polymorphism also controls crystal habit. So the ability to grow long, thin microwires, which are ideal to observe this motion, depends on the polymorph as well. If you have the wrong polymorph, it may be reactive, but if it grows in a big block that's thick along all three dimensions, you won't see any mechanical motion. You'll still see the photochemistry, but you won't see the photomechanical response because it's too difficult to deform that brick of crystal. So polymorphism is super important, both for controlling reactivity and for controlling the habit of the crystal, so that reactivity can manifest as a mechanical response as well. So very long answer to your question. The short answer is yes, totally important. And you know, you want to look for a polymorph that's less dense, or at least opens up some space next to the reactive unit of your molecule.
Mm-hmm.
Thank you. I do not see any more questions.
So if we do not have more questions, then thank you very much once again, Chris, for this really fascinating lecture.